Okay, so let's take a look at this problem. We've got three charges. Let's go ahead and label whether they're positive or negative because that's going to be important. So this guy's positive, Q2 is negative, and Q3 is positive. Okay, we're going to find the net force on Q2 and then as a separate problem, the net force on Q3. So let's look at Q2. Let's draw a free body diagram for him. 1 and 2 are opposite charges. So everybody's glued down here. In the real world, if we just had these three charges and we let them go, everybody would move. What we're doing for the moment is 1 and 3, they're stuck. They're glued down. We've placed Q2 right here, and now we're going to let it go and see what the forces on it are. So 1 and 2 are opposite charges. They're going to try to attract each other. Remember, he's not going to move. We got him held down. But 2 is going to get pulled towards 1 because they're opposite charges. Let's call that F1 on 2. So we're going to have a force like this, F1 on 2. 2 and 3 are opposite charges. They're going to attract each other. So we'll have F3 on 2 here. That's going to go straight up. Draw that straight up. F3 on 2. We need to find both of those as vectors. We got to be careful with our pluses and minuses. And then we're just going to add the vectors together as vectors. So in magnitude, I don't care about pluses or minuses here. In magnitude, F1 on 2 is K, absolute value Q1, absolute value Q2, over their distance, R12 squared. Okay, so we're told the distances here. This is 0.7 meters, and this distance between 2 and 3 is 0.4 meters. So the distance between 1 and 2 is 0.7. All right, K is 8.99 times 10 to the 9th. Q1 is 2.6 microcoulombs, so times 10 to the negative 6th. Q2, don't care about the negative. We're never, ever, ever going to plug negatives into Coulomb's law here because this is magnitude. We take care of the positives and negatives by looking at the picture. Q2 was 0.8 times 10 to the negative 6th because it was microcoulombs, and then divided by that distance, 0.7 squared. Okay, we're going to type all that in our calculator, 8.99. Now, to do scientific notation, we're going to use the EE button here. So, second EE, 9. That means times 10 to the 9th. Times 2.6 EE. Negative 6, not minus 6. Negative 6. Times 0.8. EE, negative 6. Divided by 0.7 squared. 0.0382. Okay, that's the magnitude. I can look at the picture and see that that entire force is all in the x direction. There's no y component to this force right here. So as a vector, F12 will be negative 0.0382, comma, 0. And that's measured in newtons. Negative because it's pointing to the left. I got to put in that negative myself by looking at the picture. Why is it negative? Because these are opposite charges, and 2 here is attracted to 1. It wants to go to the left. Okay, now let's do in magnitude 3 on 2. That's going to be K, 8.99 times 10 to the 9th. Q2 and Q3. So I'll do it in the other order. Q3, 1 times 10 to the negative 6. That's Q3. Q2, still 0.8 times 10 to the negative 6th. Over their distance, 0.4 squared. Right, now, if I'm really careful here, I can just go back and edit my last entry. You always want to be careful with that, though. So I'm going to hit second enter to get to my last entry. And the only thing I need to change is this. Instead of 2.6, I've just got a 1. So just because I don't feel like deleting stuff, 1.0. That one stays the same. And then the distance was 0.4. So 0.04495. Was it 0, 0? No, just 1, 0. Now, I have to look at the picture and figure out my direction here. So as a vector, that vector there points straight up. No x component at all, and the y component's going to be positive. So that's 0, comma, 0.04495. And that again is measured in newtons. So then on Q2, F net, we just add those vectors as vectors. Add the x's. I'll actually write all this out. Negative 0.0382 plus 0, comma, 0 plus. So that will be this vector. And let me make sure I got that one right. 4495, yes. But it doesn't ask for the vector. It asks for the magnitude. So the net force there in magnitude, we just use Pythagorean. Remember, with Pythagorean, a negative squared is a positive. So don't worry about that negative there when you're finding the magnitude. So just 0.0382 squared plus 0.04495 squared. And we can type that in our calculator. And I got a little squared button right there. And I get that number, which is exactly what they have for the answer. Now there's a little rounding going on. Whoever wrote this problem probably used 9 times 10 to the 9th for K, but it would absolutely give me credit for this. Okay, so that's just rounding error. Okay, now let's find the net force on Q3. Oh, so let's write down what we got there. 0.059, I'll just call it. Okay, now on Q3. All right, so I'm going to redraw the picture here. What are the directions of the forces on Q3? Here's our arrangement. These two are positive, that guy's negative. These two are going to be attracted to each other. So now 1 and 2 are glued down. They can't move. We're only looking at what's the initial force on Q3. So here, I'll color code this. These two are opposites. They're going to attract. So we're going to have F213 pointing down, straight down toward there. And these guys are going to repel each other because they're both positive. So we'll have F1 on 3 is pointing up at some angle. And we're going to have to find that angle. So if we draw a free body diagram here, here's Q3 right at the origin. We're going to have two vectors, F2 on 3 pointing straight down, and F1 on 3 pointing up at some angle. We're going to have to find that angle right there. F2 on 3 is easy. It's equal and opposite to F3 on 2. That's a third law pair there. We've already found that. Just is going to be a negative instead of a positive. F2 on 3 is the opposite of F3 on 2. So that will be 0, negative, and I forgot what the number was, 0.4495. Okay. 1 on 3 is the one where we got to do some work. So we're going to have to look at this triangle. This is a right triangle here. This was 0.7. This was 0.4. I'm going to have to find this angle here because that's the same angle up here that force is going to make. That's this angle theta right there. I have to find that angle because I'm going to have to do some trig. And I have to find this side because I need the distance between 1 and 3. So this here we'll call R13. That's the distance between them. So Pythagorean there, R13 is square root 0.7 squared plus 0.4 squared. Oops. 0.4 squared. So we'll call that 0.806. That should be rounded enough. That's the distance between them. The magnitude of the force, F1 on 3 magnitude, will be K, Q1, Q3. Then I wrote it 2, 3. Over their distance squared. So again, whoever wrote this problem probably used 9 times 10 to the 9th. That's usually good enough. Q1, 2.6, Q3 was 1. And then their distance, 0.806 squared. Now what I could have done, since I knew I needed R13 squared, I could have just done what's inside there and not taken the square root and then squared it. And my answer may have been a little more exact, but this will be good enough. I just want everything to be on the screen here. All right, so 9 times 10 to the 9th times 2.6. Notice all these charges I'm putting in as positives. That was 2.6. We never put negatives into Coulomb's law. We're finding a magnitude here. Times 1. E negative 6. Divided by 0.806 squared. 0.036. Okay, that's the magnitude of the force. I got to find this angle. So I could do, say, tangent of theta will be 0.4 over 0.7. So theta here, I'm in a right triangle. I can trust my calculator to do an inverse tangent. Inverse tangent, 0.4 over 0.7. I'm going to make sure I'm in degree mode. As long as I were consistent later, it wouldn't have mattered. But I am going to make sure I'm in degree mode. And then do inverse tangent, 0.4 divided by 0.7. And I get an angle of 29.74 degrees. Okay, now I'm ready to find the components of my vector. So I've got F13 pointing up at some angle. I know the angle here, 29.74 degrees. This will be the x component of that vector. This will be the y component. Now, this is important because there are different variations of this question where these two are opposites. If these were opposites, then we'd be attracted down, and both my x and my y components would be negative. Like, you have to draw the picture. You have to look at your components and see if they're positive or negative. In this case, because both of these guys are positive, Q3 wants to run away. So he's going to point up like that. If he were pointing down, he would have a negative x and a negative y. But it would be the same numbers that we're about to come up with. Okay, I know that magnitude there, 0.036. Now I can just use trig. I know that, for example, sine of that angle should be the y component over the magnitude. This is F1 on 3. So just opposite over hypotenuse. Multiplying this over, we get Fy is the magnitude times the sine of 29.74 degrees. Now again, it's from the picture that I know that's going to be a positive. If my vector were pointing down here, I'm going to draw this in and erase it. But if my vector had pointed down like this would still be a 29 degree angle in here, but this would be some negative y component, and this would be some negative x component. But that's not what we have. All right, so let's type this in our calculator. The magnitude, which is on my screen now, times sine of 29 point. Oh, no, sorry, I lied. That is the angle. The magnitude is not on my screen right now. That was 0.036 times the sine of that angle. And I could just do second answer, or I'm just going to type it in. 0.0179. Fx. Like, it should be obvious here. If y went with sine, x is going to go with cosine. That's not always the case. I know that because I know trig. I'm just using the trig. I know sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. So this would be 0.036 cosine of 29.74 degrees. Close it. 0.031 Okay, so then my vector, this is vector F1 on 3, has a, you got to be careful here. We all tend to have sine as our favorite out of all the trig functions. I do this all the time. I do sine first, so I always end up finding Fy and then Fx. And then I get in the habit of writing this one comma that one. You got to be careful here. That's my x component, comma, my y component. Okay, so I'm going to circle that. Now I got to add these vectors together. So I found two different vectors. Here was the other vector. I'm going to recopy him down here. 0, negative. So recall, F2 on 3 was 0, negative 0.04495. Now I just add the x's, and I'm going to write it out. 0.031 plus 0, comma, 0.0179 minus 0.04495. Obviously here we get 0.31. I need my calculator for that one. 0.0179 minus 0.04495. My net y is in the negative. 0.2705. Make sure I got that right. Okay, so let's think about what we just did. I've got one vector pointing up that way, one that way. Those are going to add together. Remember how to add vectors? We add them tip to tail. So we've got 1 on 3 plus 2 on 3. And he's a little longer than that. The net force is going to point down like this. It's going to have a positive x and a negative y. So really we're taking this guy over here and moving it under this one. You start at the beginning, end at the end. So my net force is going to point toward the positive x, but the negative y. Which is what I got. And then we find that magnitude. So the magnitude of the net force on Q3. So again, I'm just going to write this here because I'm going to upload this document. This is on Q3. Will be square root of 0.031 squared plus 0.02705 squared. I'm not going to put the negative in here because when you square a negative, it's positive anyways. Two 705 squared 0.041 newtons. And let's see what the correct answer was. Oh, look at that. 0.041. Now, of course, there's a little rounding error in here. They got 139, and what did I get? I'm close enough. It would have given me credit for this. So that's just rounding error. That's not using the same number of sig figs that they used there. Okay, now I do want to point out there are many variations of this problem where these numbers, these signs are changed around. You have to draw out your free body diagrams here see which direction Q2 is being pulled or pushed in. Determine, are those going to be positives or negatives? Same thing when you do the second part here, Q3. Again, if this had been a positive, then Q3 would want to go up to run away from him. If this guy had been a negative and a positive, they would have been attracted, so Q3 would have tried to go down. If they were two negatives, if these two were negatives, Q3 still would have tried to go exactly the way it did. It would have tried to run away from Q1. Okay, I hope this was helpful.